In this video, we begin Chapter 11, looking at more advanced models for covalent bonding. Before we begin, we can review where we've been. Lewis dot structures and BSEPR, they're nice first simple models for covalent bonding. They provide a lot of insight into shapes and some reactivity of molecules. Methods are very useful for organic compounds. But even for organic compounds, there are shortcomings. These models don't provide any insight into the electronic structure of molecules. In particular, atomic absorption and atomic emission spectra are not observed for molecular systems. Molecular systems have very different absorption and emission characteristics compared to atomic systems. Therefore, we need some model that allows us to begin to expand into more complex properties, including electronic structure and behavior. So we're going to begin looking at two more sophisticated models for covalent bonding. We're going to look at valence bond theory, which involves what it will be termed orbital hybridization, and it will allow us to distinguish the various types of bonds. So, for example, single bonds will have two types of bonds involved. And then we'll go on to a more advanced version, which is called molecular orbital theory. We'll do just a very simple beginning to this, but this allows us to understand electron wave delocalization in both compounds and in solids. Here's our outline. We'll begin with valence bond theory and we'll discuss orbital hybridization. We'll talk a little bit about what we'll call bond symmetry, and then we'll look at modes of orbital overlap and the types of covalent bonds. Then we'll look at molecular orbital theory and electron delocalization. And then we're going to take a section from Chapter 12, Section 12.6, which covers the solid state. In particular, we're going to look at bonding in solids. And we've pulled this into this chapter because it fits quite nicely in as a follow-on to molecular orbital theory. So we'll start with valence bond theory. The basic principle of valence bond theory is that a covalent bond forms when the orbitals of two atoms overlap, and then a pair of electrons from the reacting atoms occupy the overlap region. The space formed by the overlapping orbitals can accommodate a maximum of 2 electrons, and these electrons must have opposite spins. The greater the orbital overlap, the stronger the bond. And the extent of orbital overlap depends on the orbital shape and the orbital direction. So let's take 3 really simple examples to start off with. First, we have the formation of a hydrogen molecule from 2 hydrogen atoms. We see a representation here with these 2 balls. We have a hydrogen atom in its 1s electronic state, and another hydrogen in its 1s electronic state. When the 2 hydrogen atoms become close to one another, these 1s orbitals then overlap one another. And then when they overlap, that's the region where the electrons can go and pair up. Next, we have hydrogen fluoride. And this bond forms when the hydrogen 1s orbital overlaps with the half-filled fluorine 2p orbital. Remembering that fluorine's outer electron configuration is 2s2, 2p5, one of the p orbitals is half-filled. And so that comes in end-on. And when it comes in end-on, we have an overlapping region between the 1s and the 2p. And that overlapping region, again, is our single bond. The third example is that of the fluorine molecule, F2. In this case, we have two fluorine atoms, each with their 2s2, 2p5 electron configuration, and the half-filled 2p orbitals from each fluorine atom then interact, and as the nuclei get close, the 2p orbitals overlap. When they overlap, the electrons pair up, and the chemical bond forms. Before we leave this slide, I want you to take a look at something, and you're going to have to use your mind's eye to visualize this perspective. But for each molecule, imagine looking down the axis of the internuclear interaction. So that's going to be in the plane of the slide. If you could look down the axis of interaction for all three of these systems, the overlap region would look like a circle. So you're looking perpendicular, to your vision right now. So you're looking straight on at the slide. Imagine looking down the plane of the slide. The overlap region is going to be a circle or radially symmetric. And that turns out to be a key element. And this will be discussed in our next video after this one. The symmetry of overlap of the atomic orbitals tells us the type of bond we have. And so sigma bonds have what we call radial symmetry. That is, when two spheres overlap, the overlapping region observed down the axis of the bond is radially symmetric. It's a circle. Like the two s orbitals in the hydrogen atom interaction, their overlapping region looks like a circle. So the overlapping region overall is a disk, but then if you look from the disk from the top, you'll see it's circular. When two atomic p orbitals overlap end to end, the overlapping region, again, is radially symmetric. And if you have a p orbital, or a d orbital for that matter, come in end on and interact with an s orbital, you will get radial symmetry. It'll look like a circle, and the center of the circle will be the center of the bond, and that circular region is the region of overlap of the two orbitals. We'll see later on we're going to have what we call pi bonds. So if you have a double bond, you'll always have one single bond and one pi bond. You can't have two sigma bonds in a double bond. You have to have one sigma and one pi. And for a triple bond, you'll see you'll have one sigma, and then you'll have two pi's, but the two pi bonds will be in different planes. So the pi bond shows planar symmetry. And this would occur if you took two p orbitals and overlapped them side on. And then if you look at the overlap region, that would have a mirror plane symmetry. So now we're going to look at what we're going to call orbital hybridization. This is a key concept. In general, the orbitals that form when bonding occurs are different from the atomic orbitals in the isolated atoms. And we're going to see that this is going to relate back to VSEPR. If no change occurred, we could not account for the molecular shapes that are observed, and that's our connection. So the orbitals on each individual atom will mix within themselves. So an individual atom's s, p, and d orbitals will mix, hybridize, and convert into a different set of hybrid orbitals when the bonding is occurring. And that allows us to account for molecular shapes and symmetries and overlap. So this is connecting VSEPR to valence bond theory. Once you've formed these hybrid orbitals, they're going to have a series of characteristics. the number of hybrid orbitals equals the number of atomic orbitals that are mixed. So if you have one s and two p orbitals that mix together, then you're going to end up with three hybrid orbitals. There'll be three sp squared or sp2 hybrid orbitals. The type of the hybrid orbitals formed varies with the types of atomic orbitals mixed, and we simply label them by the number of each atomic orbital that we use. The shape and the orientation of a hybrid orbital maximizes overlap with the other atom in the bond, and this ties back to our concepts of symmetry. So this table here provides an important relationship for you to use in connecting via CPR and hybrid orbitals on a central atom in covalent bonding. So remember, the central atom hybridizes its own atomic orbitals to produce hybrid orbitals that will maximize overlap for covalent bonding. So the first column here tells us the electron group arrangement. And you know from chapter 10 how to deduce electron group arrangements to use in VSEPR, right? So you know how to make an electron group arrangement. And then we have linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Next up, we have the atomic orbitals that are involved in these types of electron group arrangements. So for any atomic orbital, we have to have as the number of orbitals that will be associated with the number of electron groups in the electron group arrangement. So for a linear system, we have two electron groups. Therefore, we have one s and one p. And the third column shows us the hybrid orbitals that are produced. We get two sp hybrid orbitals. For a trigonal planar system, of course, there's three electron groups, so we have 1s and 2p atomic orbitals that mix to form three sp squared or sp2 hybrid orbitals. For a tetrahedral system, we have four electron groups. Therefore, we need 1s and 3p atomic orbitals. They will mix to form four sp3 or sp cubed hybrid orbitals. The trigonal bipyramidal system has five electron groups. Now we need to use d orbitals. And so, of course, we don't see trigonal bipyramidal structures for period 2 in the periodic table. We have to get to period 3, where the 3d orbitals can get involved. So we have 1s, 3p's, and 1d to make 5 sp3d hybrid orbitals. The octahedral electron group arrangement has 6 electron groups. Therefore, we need 6 atomic orbitals. So we have 1s, 3p's, and 2d's. This provides us 6 sp3d2 hybrid orbitals. Let's take as an example beryllium chloride. Remember we looked at beryllium chloride earlier. Even though it's a metal and a non-metal, it has substantial covalency in its bonding. And beryllium chloride has 2 electron groups around the central beryllium atom. With 2 electron groups, we know that that is 2 atomic orbitals that are needed, so we have an s and a p. We will produce 2 sp hybrid orbitals. So we see up above, we've got our atomic orbitals. We've got a 1s and a 1p. That's the 2s, the principal quantum number 2s, and the principal quantum number 2p orbitals. So those s and p's mix to produce 2 sp hybrid orbitals. And so down below, we can see the initial atomic orbitals that are involved. So on the left-hand side at the bottom, we have an isolated beryllium atom. Its electron configuration is 2s2. All of its 2p orbitals are empty. In this case, we mix these atomic orbitals to produce the hybrid orbitals. So on the right-hand side, then, we have our hybridized sp orbitals. Notice that the energy, and in this case, there's a vertical axis that implies energy. The 2s, of course, is below the 2p, but the sp hybrid orbitals are between the 2p and the 2s orbitals. So the sp is a little higher in energy than the s, but a little lower in energy than the p. And these each have one electron in them. Now, we'll see later on, they don't have to follow the Aufbau principle because they're involved in bonding, so they become a little more complex. The 2p orbitals that are not hybridized remain at the same energy. They're at the top, and in this case, they're empty. Here we see a picture of the interaction of the sp hybrid orbitals with the chlorine p orbitals. So the chlorine has a empty or a half-filled 3p orbital, and that half-filled 3p orbital interacts with the sp orbital, and those two interact end-on. So they actually have radial symmetry to them. So this is a sigma bond. So we form two sigma bonds, one between the beryllium and chlorine, and the other between the other chlorine with the beryllium atom. Next, let's go to boron trifluoride, BF3. If we remember BF3, it's a trigonal planar molecule. It has a trigonal planar electron group arrangement. Therefore, we're going to need how many electron groups? We need 3. And we have how many orbitals? We'll need 3. So we mix 1s and 2p orbitals, which gives us 3 sp2 hybrid orbitals. The third p orbital remains unhybridized and empty. So we take our boron central atom. Our boron central atom has a 2s2 2p1 electron configuration. Here we need to have 1 of the s and 2 of the p's. We pull those together to form 3 sp2 hybridized orbitals on the boron atom. Each one will have 1 electron in it, and then each one of those electrons will interact with the fluorine half-filled 2p orbital to form a sigma bond. We can see that here. We see the boron trifluoride. If we had gone through and done the via CPR, it would be trigonal planar, and it's trigonal planar electron group arrangement. That's the key here. And the remaining unhybridized 2p orbital is perpendicular to the plane of the molecule. We can see in each case a half-filled sp² hybrid orbital interacts with a half-filled 2p atomic orbital on fluorine. That overlap brings the 2 electrons together. The 2 electrons sit in the overlap region, paired up, forming a sigma bond, or a single bond. The 3 sp2 orbitals point to the corners of an equilateral triangle with their axes 120 degrees apart. Each half-filled sp2 orbital overlaps with the half-filled 2p orbital on the fluorine. Next up, we have methane, CH4. Methane is a tetrahedral molecule from a tetrahedral electron group arrangement. That means we have 4 electron groups in this molecule on the carbon atom. If we have 4 electron groups, that means we'll need 1 of the s's and 3 of the p's. We mix these together and we produce 4 sp3 hybridized orbitals. Notice that they're closer in energy to the p's than the s, since we're mixing in more p character than s character. Each one has 3 parts p, 1 part s. Then the 4 sp3 orbitals adopt a tetrahedral shape. They go to the corners of a tetrahedron. Carbon in methane has atomic electron configuration, valence configuration of 2s2, 2p2. Those 4 electrons, so we have 4 valence electrons from carbon. One goes into each of the hybrid orbitals, sp3 hybrid orbitals on the carbon atom. And each sp3 orbital, which is half filled, can then interact with a hydrogen 1s orbital, which is half filled. And that produces our 4 sigma bonds. Let's take a step up to a system that's a little bit more complicated, a little bit different. That is ammonia, NH3. If you remember back to NH3 in Silverberg and Amateus, they did the electron group arrangement. This turns out to be a tetrahedral electron group arrangement with 1 lone pair. Therefore, the structure would be a trigonal pyramid. That's the molecular structure. When we're looking at valence bond theory, we care about the electron group arrangement. That will determine the orbital hybridization. So for 4 electron groups in this tetrahedral electron group arrangement of ammonia, we'll need 1s and 3p orbitals to make 4 sp3 hybrid orbitals. The orbitals here look very similar to those on methane. The difference occurs because the nitrogen atom electron configuration is 2s2, 2p3. That tells us there's 5 electrons. It's group 15. So your 5 electrons in group 15 then have to go into 4 hybrid orbitals. Therefore, 2 of the electrons must be paired up. The other 3 electrons are in separate orbitals. The 2 electrons that are paired up are the lone pair. The other 3 electrons go into the nitrogen-hydrogen bond overlap. These are all radially symmetric and sigma bonds. They're single bonds. The nitrogen lone pair occupies 1 corner of this trigonal, or this tetrahedral electron group arrangement by filling up an sp3 hybrid orbital. Next, we can look at water. We looked at fluorine oxygen difluoride, which is the same principle as water. Water was also shown in the ESCPR section of Chapter 10. And water has an tetrahedral electron group arrangement. There are 4 electron groups around water. 2 oxygen-hydrogen bonds, 2 lone pairs. We can see how this arises then using valence bond theory. The oxygen atom has an electron configuration of 2s2, 2p4. We need 4 electron groups because we have a tetrahedral electron group arrangement. We need 4 hybrid orbitals. So again, we have our sp3 hybrid orbitals, 4 of them. Now, though, we have 6 electrons to put in here, so we must have 4 of them paired up, 2 lone pairs. We have 2 pairs of lone pair electrons and then 2 bonding electrons. Each of the individual bonding electrons can interact with the hydrogen 1s to produce a single bond. Now we'll move out of period 2 into period 3. We'll look at phosphorus pentachloride, PCl5. This is a covalent compound. PCl5 has trigonal bipyramidal electron group arrangement. 5 electron groups for the 5 phosphorus chlorine bonds. In order to get 5 hybrid orbitals, we run out when we have the 3s and 3p. We've only got 4 there, so now we have to begin using the d orbitals on the PCl5. So we have our 3s2, 3p3 electron configuration, but we add in a 3d orbital. And that gives us 5 sp3d hybridized orbitals on the phosphorus atom. Now we know that phosphorus is group 15, and it has 5 valence electrons from its 3s2, 3p3 electron configuration. Each of those electrons goes into a separate sp3d orbital. So you can see why we see expanded valencies for the group, the period 3 through 6 elements. Period 2 elements have no d orbitals. There is no 2d orbitals to mix in. It's only when we get to period 3 that we have the 3d available. Period 4 has the 4d, period 5 has the 5d, and so forth. So now we have 5 sp3d orbitals. That way we can have 10 electrons around the phosphorus in its compounds. The last one we'll look at is the octahedral system. The octahedral system has 6 electron groups. With 6 electron groups, we need 6 orbitals. Therefore, we need an s, 3 p's, and 2 d's, giving us the sp3d2 hybridized orbitals. For sulfur hexafluoride, we have an octahedral electron group arrangement. Sulfur has a 3s2, 3p4 electron configuration. That's 6 electrons. Those 6 electrons then are spread across the 6 sp3d2 hybrid orbitals. Each one of those orbitals interacts with a fluorine atomic 2p orbital that is half filled to produce 6 sigma bonds. And of course, in this case, then sulfur would have 12 total valence electrons in this compound, the expanded valency coming from the d electrons, which can hold more electrons. Here's a summary table that illustrates what we talked about earlier. At the bottom of the table is the electron group arrangement: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. And the table lists the number of the types and numbers of atomic orbitals involved, the hybrid orbitals that are produced, and the unhybrid orbitals that remain. We'll look at a number of examples of these when we go to the mechanics videos.